right, let's start this segment talking about what we know about E. All right, and there's some things we've already seen on Lab 1. Right, we already saw that the natural log of E was 1, not a big surprise. But when we looked at how we defined natural log and what we were doing in Lab 1, remember we defined E this way, that the area under the curve of 1 over x, the area from 1 to E has a value of 1. All right, and so over here on the right-hand side, I drew a picture of that. And notice I labeled the area as 1, right? The highlighted area has a value of 1. So you already have this in your notes. It wouldn't hurt if you wanted to write it down again, because this would make a good test question, right? Is to give me a college definition of E. Tell me something about E other than just it's 2.72. Now, other things that we should have concluded about E, and some of this are things that you would know from high school. For example, you've already talked about the idea that e to the x is the inverse of the natural log function. All right, and again, that's something that you would already have seen. And so if I drew a picture, right, here's my natural log function over here, right, passing through the point 1, 0. And so if two functions are inverses of one another, that means I can just reflect this function through the line y equals x. And here's my function e to the x. Of course, passing through the point 0, 1, because e to the 0, right, anything to the 0 power is 1. So all exponential functions pass through the point 0, 1. And I think you're familiar with this as well. Since they are inverses of one another, we get this relationship, that the natural log of e to the x is just x. And the natural log, e to the natural log of x is x. And other things, well actually before we go on and talk about what we concluded thus far, other things that we should be able to do are use e and natural log to solve equations when the need arises. And so say we wanted to solve this equation for t, right? E to the 3t equals 8. So what we could do to isolate the variable t is we could take the natural log of both sides. All right, so in this case, take the natural log of both sides. Right, on the left-hand side, I would be left with 3t, right, since e to the natural log, or natural log of e, right, those undo each other and leave me with just 3t equals the natural log of 8. And then we can leave our final answer in this form. All right, that would be an acceptable final answer. I could change it to a decimal if I wanted to, but that would be an acceptable way to leave my final answer. Now, another type of equation where we're going to use natural log to help us is if we were solving something like this. All right, and we know 2 to the 4th equals 16, so I'm expecting an answer a little bit less than 4. But anytime I want to solve for x and x is an exponent, all right, I always tell students if we have an exponent problem, both literally and figuratively, right, because literally we have a problem with an exponent in it, but figuratively we have a problem as in a problem like I'm not sure what to do, right? So every time we see a problem with exponents, we should think of natural log. All right, so if we take the natural log of both sides, right? And that's all because natural log is the only function we know that lets us take this exponent, right? And by our rules of logs, we can rewrite that as x times natural log 2 equals natural log 15. So x equals natural log 15 over natural log 2. And I did take the final step of changing this to a decimal. to show that x is equal to 3.9. All right, so about what I was expecting. So anyway, let's go on and talk about what we learned in the last class about e. All right, so this is how we would use e in natural log. And again, I think you did do problems like these at some point in your pre-calculus work or high school work. But something else that we saw with e is it is an exponential function. And when we talked about, well, what's so special about this number 2.7, right, we were able to conclude that it's an exponential function, which is its own derivative. And the point that I didn't quite get to make in class before we ran out of time, we were using the limit definition to find the derivative of 2 to the x and 3 to the x, right? And so we were using table on our calculator, and we were estimating, so the derivative of 2 to the x is equal to 2 to the x times 0.69. And the derivative of 3 to the x is equal to 3 to the x. Oh, I need a 3 to the x in here. Derivative of 3 to the x is equal to 3 to the x times 1.09. And what you didn't get to see is that 0.69 is actually the natural log of 2. And 1.09 is actually the natural log of 3. All right, so if you don't believe me, take out your calculator and test it out and see. But then things that we should conclude from the lab then, we are able to conclude that when we take the derivative of an exponential function, and keep in mind we are only considering values of a that are greater than 0. All right, if you try to type it on your calculator and do the quantity negative 2 to the x and look at a graph, it's not going to work out. You're going to see errors in a lot of points. All right, so we're discussing only values of a greater than 0. So this is the derivative of a to the x. And then being consistent with this rule, right, when we come down here and say, okay, well then by this same rule, what is the derivative of e to the x? Well, e to the x then, its derivative would be e to the x times the natural log of e, which of course is e to the x. All right, so that's what makes e to the x so special. Now, if we wanted to find the derivative of, say, something like e to the 3x squared. All right, so again, I've got a composition of two functions. So I took the function 3x squared and I put that into the function e to the x. So we have a composition of two functions. So we know according to the chain rule, right? So by chain rule, to find the derivative of e to the f of x, right? So e would be my outer function, f of x would be my inner function. So f of x is the function that I put into the function e to the x. So I need to do derivative of the outer, keep the inner the same, times the derivative of the inner. All right, so this is how I would find the derivative of e to some function of x. So let me slide back up to this example. So that means that I would have e to the 3x squared, right? There's my e to the f of x, times the derivative of the function, which would be 6x. All right, and in writing my final answer, coefficients belong out in front. So normally this would be written like this. Let's put the 6x in front and have the e to the 3x squared last. Now, let's consider the chain rule then with a to the f of x. All right, so far we have looked at the derivative of, 2 to the x, 3 to the x, right? Any power, any value of a greater than 0, to the x, right? So we were just able to see, okay, this derivative is a to the, well, hang on, let me do this. If it's just a to the x, I mean, we just had this a minute ago, but quickly, let me do this again. This derivative is a to the x times the natural log of a, right? So if I have some function of x, what I have to do using the chain rule, then this would be my outer function. A to some power is my outer function. My inner function, again, is f of x. All right, so I would need to do a to the f of x times natural log of a times the derivative of that function. This, of course, can go in any order, right? If I have a product, it doesn't matter what order I write that product in. So let's look at an example. If I wanted to find the derivative of 5 to the cosine 2x power. All right, so following the law above, I need to keep a, so a in this case is 5, so a to the f of x times natural log of a, which is natural log of 5, times the derivative of the function. And so I purposely picked something I think people need a little review on in Calc 1. Remember, this itself requires the chain rule. Cosine is my outer function, 2x is my inner function. All right, so derivative of cosine, let me put these all in parentheses. Derivative of cosine is negative sine. All right, so I get negative sine 2x. But then I have to do times the derivative of the inner. So times the derivative of that inner function would leave me with times 2. All right, and again, coefficients belong out in the front. All right, so I want that 2 out in the front instead of tagging along at the end. But again, any order that you put this in is fine, certainly, because it's a product. Now, let's look at an example with integration. And it's not going to surprise you that since e is its own derivative, right? E is its own derivative, so when I go to integrate, I have to ask myself, well, what function has e to the x as its derivative? And that is, of course, e to the x plus some constant. And if I were integrating, say, a to the x, I have to ask myself, what function has this as its derivative? So the derivative of a to the x is a to the x times natural log, right? So if I don't want the times natural log here, that means that that would have been divided out. All right, so the antiderivative, and again, if you don't believe me, then actually take the derivative of this, right? Because you'd get a to the x times natural log of a. These would cancel. I'd get back to this. And I'm not quite sure why this is hard for students, but I know last year, I remember being kind of surprised. I had a very basic question on a quiz, you know, like integrate this, right? And it was one of the most missed problems. So all this is 3 to the x over natural log 3 plus c. All right, so I don't know if people just didn't remember this rule or what exactly confused them so much, but I know that this was a very highly missed question on last year's quiz. So let's do one example with u substitution. So to be able to use u substitution, you have to see the derivative of u as part of your integrand. And I'll give you a little hint and say when you're doing integrals involving e, if the power is anything other than x or r or whatever the variable is, then this power would be your u. All right, so I would let u equal radical r. And last year in Calc 1, whenever I teach Calc 1, I always tell my students to memorize the derivative of radical x. All right, because we see that over and over again. So if you guys can't do this one very quickly, recognize this very quickly, certainly you could raise that, x to the positive 1/2 and use the power rule and decrease the power by 1. But this comes up so many times that I want you to memorize that the derivative of radical x is equal to 1 over 2 radical x. All right, so I just have an r instead of an x. So my derivative would be 1 over 2 radical r dr. And if you solved this for dr, all right, so if I multiplied both sides by 2 radical r, so I'd get 2 radical r du equals dr. All right, so that means I can, let me put a little arrow here, that this integral is equal to, so I would have e to the radical r over radical r. In place of dr, I can put 2 radical r du. I'm sorry, this should be a u. All right, I substitute in for u. Cancel. All right, so then I have the integral. I'm going to put that 2 out in front. 2 times the integral e to the u du. Well, that's just e is its own derivative. E is its own antiderivative. So that's just e to the u plus c, where I plug back in for u. So u was radical r. All right, so let's move on then and talk about